Hello everyone, good morning. Welcome to Gate Academy Global. If my audio and video both are clear, just confirm me. Just confirm me both audio and video are clear or not. And then we will start today's session. Okay, just confirm me. Just confirm me everything are perfect or not. Okay, till now what we have studied. Okay, everything is perfect. Thank you. Till now we have studied all the basic part from the digital, that is logic gate, basic number system, two's complement, binary codes, K-map, boolean algebra, and also in previous classes we have discussed adder, half adder, full adder, half subtractor, full subtractor, as well as a binary parallel adder. That is a binary parallel adder. In binary parallel adder we have also discussed many number of problem from the propagation delay, and you should be expert in that part. Patiently you have to watch that lecture patiently, and you have to try some example from your side, and you have to solve previous year question too. Later I will discuss some more problem from the adder topic. Okay, so after completion of combinational circuit I will conduct 1-2 classes for the problem discussion. Okay, in that class I will also discuss more number of problem from the adder circuit. Clear this thing? Okay, yeah, good morning everyone, good morning. Okay, now today's session I am going to start. So in today's session BCD adder you have to study. Okay, now I am going to conduct from the today's session, that is decoder circuit. So in today's session I am going to start decoder, and this is very important circuit. Decoder is very important. Why decoder is important? After some time you will get the answer. After some time you will get the answer. So now we have to study decoder, encoder, multiplexer and demultiplexers. So here decoder and multiplexer are more important than encoder and demultiplexer. Why? You will get answer. Okay, definitely after some time you will get answer why decoder and multiplexer are more powerful. Okay, now so first you should know what is the decoder circuit. Decoder circuit is nothing but, suppose I am conducting a one digital block. Okay, inside the digital block can be only logic gates, and which logic gate? Generally we target NAND gate generally. Okay, so now this is a one digital block. How we can represent decoder? Decoder is nothing but n cross 2 raised to power n line decoder. What we call decoder? 2 raised to power n cross 2 raised to power n line decoder. How many number of input here? N line input. How many number of input here? Here input is n line. And how many number of output lines? How many number of output lines here? 2 raised to power n output lines. 2 raised to power n output lines. And how many number of input lines? Here I can say n input lines. N input lines. And one more signal you can consider here to enable or disable the decoder. You can also assume here one more signal, and this is for the enable signal. This is for the enable signal. Clear this thing? So this is the basic structure for decoder circuit. N number of input, 2 raised to power n number of output, and one enable circuit. Clear? Now I am going to take one example. I am going to take one example. One example I am considering 2 cross 4 line decoder. And I can also say this is nothing but 2 to 4. This is also called 2 to 4 line decoder. Okay, now we have to study this. Then how many number of input lines here? How many number of input lines? Input lines is only 2. How many number of output lines here? That is 4. 1, 2, 3 and 4. This is, you can say, 2 cross 4. Can I consider one extra signal? You can treat this signal enable as a switch, power switch you can assume, but in general this enable signal is received from the microprocessor. This enable signal you receive from the microprocessor, and this enable signal can be in any form. Either it can be treated, means enabled by 0, or it can be enabled by 1. It can be anything. So this enable signal can be either enable this decoder by 0 or by 1, by anything. Okay, now so here I am considering one enable signal, and that is E. This signal is nothing but enable. This is the two number of input. Suppose I am going to assume this is X and this is Y. Suppose this is X and this is Y. Here MSB, you have to write MSB. I am considering this is MSB and this is LSB. So by this 0 and 1 you can find out this is 0 means LSB, this 1 means MSB. Here you can also write, I am writing here 0, this is 1, this is 2, this is 3. This means this is the LSB and this will be the MSB. Okay, what will be this output? I can write this is nothing but D0, this is nothing but D2, this is D2 and this is D3. Okay, this 4 output I am going to write for the decoder output D0, D1, D2 and D3. Now what is the actual meaning of decoder and how this circuit will work? This is the very important thing, how decoder will work. So decoder, how decoder will work? First this decoder should be enabled. This is the first condition. Now if XY, how many different XY can be possible? 0, 0, 0, 1, 1, 0 and 1, 1. So what decoder will provide you? If XY is 0, 0, then this LED will be on. This LED will be on. So here you can treat this 4 output is possible. In one time only you will get one output. This is very important thing. So you can write here in a decoder circuit, in one time, or you can say at any time only one output is possible. Only one output is possible. Okay. So if, and that will depend on the input. So if input is 0, 0, your output D0 LED will be glow. If this is 0, 1, D1 LED will be glow. If this is 1, 0, D2 LED will be glow. And this is 1, 1, D3 LED will be glow. So what will be the truth table for this? Truth table can I write here, first enable signal and input is X and Y. Input is X and Y. And this is your output. Here can I write output D3, D2, D1 and D0. Can I write in this way? Now if enable is 1, X and Y is 0, 0. Enable is 1, X and Y is 0, 1. Enable is 1, X and Y is 1, 0. And if enable is 1, X and Y is 1, 1. Clear? Now if X, Y 0, 0, then this D0 will be enable and this 3 will be disable. Clear this thing? So this D0 will be 1 and remaining will be 0, 0, 0. Now if X and Y input is 0, 1, then D1 will be enable, remaining LED will be 0, 0, 0. If XY 1, 0, D2 will be enable, remaining LED will be 0, 0, 0. Now if this is 1, 1, D3 will be enable and remaining LED will be 0, 0, 0. Clear? Now if enable is 0, means this circuit is not enabled, XY can be anything. This XY can be anything. What will be the output? In this case, all the LED will be off. In this case, all the LED will be off. Clear this thing? So when you will get the output, when enable will be 1. When enable will be 1. Clear this thing? This decoder, this circuit we call active high decoder. This circuit we call active high decoder. Why we call it active high decoder? Why? Just wait for this. And this is very important thing. Many students are confused between active high and active low. Many students. So you have to concentrate on this part. Just wait. Patiently you have to wait. Clear this thing? So what decoder are exactly providing you? Just think. for x and y to input, how many max term or how many mean term can be possible? Four mean term can be possible. Which mean term? X dash y dash. So what I can write here? Now this is very important thing. What you can write here? What is the D0 exactly? D0 is nothing but, when this is 0 0, D0 will be 1, means D0 is nothing but, can I write x dash y dash? What is the D1? X dash y. What is the D2? X y dash. And what is the D3? X y. So you will get all the four mean term. Now if you will add, if you will put here 1, you will put here OR gate, and all the four mean term is available. So you can implement any boolean function. by decoder and OR gate. Clear this thing? That's why this decoder is very important. So by this decoder you can implement any boolean function, but here extra OR gate is required. Okay, I will take some example. Clear the thing? So first this basic should be very clear. Okay, now in same category, suppose for example I will change something. Then what will happen? Okay, I am going to change something like this. Suppose in same circuit, suppose for example, this is 1, this is 0, this two input x and y. You have to concentrate on this. Okay, sometime examiner can write I0, I1, input 0, input 1. Anything they can write. Sometime examiner can write in this way, I0, sometime they can write I1. So we have to concentrate on 0 and 1, which will be LSB and which will be MSB. Okay, you can also draw I0 open, I0 is upper side and I1 is downside. And here you can also write, this is 3, this is 2, this is 1 and this is 0. Here you can also write. Now this is 3, this is 2, this is 1 and this is 0, this is D0, this is D1, this is D2 and this is D3. Now if I am going with a enable bar signal, now I can write this is nothing but enable bar. Sometime examiner can also write this is enable. So you don't have to concentrate on the alphabet, you have to concentrate on the symbols. Clear? So here now this decoder will be enabled. With a 0 signal. So now if I am going to write, the name of this signal is enable. So if enable is 0, then this decoder will work, and if enable is 1, then this decoder will not be enabled. Clear this thing? In this case, what will be the truth table? So here just one thing I want to tell you. If you want to enable this decoder by 0, so this can be the first representation. Examiner can provide you here bubble and examiner can provide you this enable bar. Now examiner, if bubble are present, examiner can also write E sometime, but bubble will indicate this decoder will enable with 0 signal. Clear the thing? Sometime examiner will not provide you here bubble, but examiner will provide you here enable bar. It means again this decoder will enable with a 0 signal. Okay, so for 0 different representation can be possible, but for 1 only one representation is possible. For 1 only this is the one representation, but for 0 either they can provide you here bubble, either they can provide you here bar, or anything, either E bar or bubble. Clear this thing? Now in this case what will be the truth table? So just note down here again, this is enable and this is XY, and this is I am going to write D3, D2, D1 and D0. Please listen my word. You can write this in any order, but generally we follow D0 at upper side and D3 at bottom side generally, and here we follow MSB is upper side and LSB at lower side. Okay. Now what will this table? When enable is 0, XY is 0, 0. Enable is 0, XY is 0, 1. Enable is 0, XY is 1, 0. And enable is 0, XY is 1, 1. Enable is 1, XY can be anything. In this case, circuit will be off. Now, enable is 0 means this circuit will work. Then which LED will be on? Which LED will be on? Again, same thing. D1 will be on, remaining will be off. For 0, 1, sorry, this is D0 will be on, and for the 0, 1, D1 will be on, for the 1, 0, D2 will be on, and for the 1, 1, D3 will be on. And for the disable case, input can be anything, output will be always 0, 0, 0, 0. Okay? Anybody can tell me, should I call this decoder active high decoder or active low decoder? Anybody can tell me? This circuit is called active high decoder or active low decoder. Anybody can tell me the answer? Tell me, what should I call this decoder? Active high or active low? Active high or active low? I am waiting for your answer. I am waiting for your answer. I am waiting for your answer. Now, if this circuit is not enabled or this circuit is not enabled, and in that case you are getting output, and this output is called high impedance state. High impedance state. So this output is called high impedance state. High impedance state. Clear? And this output is also called high impedance state. High impedance state. So what is the high impedance state actual meaning? Okay, yeah, one student are saying, sir, this is active low decoder, active low. Okay, I will tell you, just wait. First I want to tell you high impedance state. What do you mean by exactly high impedance state? What do you mean by exactly high impedance state? So if any digital circuit will not work for which that is designed, in that case you can treat circuit is not operating. Either you are not providing input or you are not going to enable the circuit. In that case, all the output, if either 0 or all the outputs are 1. Two cases can be possible. All the outputs are either 0 or all the outputs are either 1. That case is called high impedance state. Clear this thing? So two cases, if circuit output depend on the input and you are not providing any input, in that case you will get all the output, either all the output are 0 or all the output are 1. But here always inputs will be present, either 0 0 or 1 0 or 1 0 or 0 0 0 1 1 0 or 1 1, anything. This circuit will depend on the enable. So if enable you are not providing, means circuit is disabled, in that case all the output can be all 0 or all 1, that is called high impedance state. Clear high impedance state? Now this circuit is not a active low decoder. This circuit is again a active high decoder. Active high decoder. Clear this thing? This circuit is again active. You have to more concentrate on active high and active low decoder. Many students are confused in this. So active high or active low, we cannot distinguish from this enable or disable signal. No, that will be decided by the output. Definition of decoder is, in one time one LED will be on, remaining LED will be off. Now you have two choices. Suppose your output is D3. So D3 LED will be on, remaining LED will be off. So on and off, how you can represent? In two way you can represent. If D3 is on and I am going to represent on to 1. So this 3 remaining will be 0. Now I am going to tell you This D3 is on, and on is represented by 0. On is represented by 0, then remaining LED will be in same category. So what will be the same category? 1, 1 and 1. So here two cases can be possible. Two cases can be possible. What is the your actual output? This was your actual output. This was your actual output. So if output is treated by logic 1. Logic 1 is called active high. Okay, this active means you can say output, and this high is representing by the 1. So if output is represented by 1, that decoder is called active high. And now if output is represented by 0, then remaining LED will be represented by 1. That decoder is called active low decoder. Clear this thing? I will take some example, don't worry. Clear? So this active high and active low should be very clear to all of you. Clear this thing? Very clear to all of you. Now I hope this active high and active low. This enable can be anything. What you want to write, you can write. So active high or active low does not depend on this enable signal. That will be defined by the output. That will be defined by the output. That will not define by the input. So here we cannot say this 0 0 means high. No. Always we can write input as it is. Output we can represent it in two different way. Okay. Now I am going to draw the circuit. Inside the circuit, what will be the inside the decoder? What will be inside the decoder? That will be exactly decide that is active low or active high. Okay. Now, so what will be the inside the decoder? Now you can implement this circuit. How we can implement circuit? This input is E and XY. You have two inputs. So can I write here? One enable signal, one X and one Y. Okay. Now suppose this is enable X. This is X. I am also going to consider here X bar, because every time X bar is required, and this is Y. This is Y. I am going to also represent here Y bar. Okay, now how many output here? D3, D2, D1, D0, 4 output. And what is your D3? What is your, okay, first I am going to write D0. What is D0? D0 is nothing but enable is 1 and XY. So what we can write D0? D0 is nothing but X dash Y dash. X dash Y dash. And how you can write X dash Y dash? That is nothing but by one AND gate. So how many AND gate is possible here? 1, 2, 3 AND gate and one more 4 AND gate. 4 AND gate is required here inside the decoder. Can I write? Now, suppose I am going to write this is D3, this is D2, this is D1 and this is D0. You can also draw D0 at upper side and D3 at lower side. Okay. Now, what will be the D3? D3 is nothing but X and Y. So, this is connected with here X. And this is also connected here with Y, and this is also connected with enable. So if enable will be 1, then you will get the output D3. Otherwise 100% D3 will be 0. Now, so every gate is first connected with enable signal. Every gate is first connected with enable signal. Now, D3 is connected with X and Y. D2 is connected 1 0. 1 0 means X Y dash. X Y dash, this is X and this is Y dash. Clear thing? Now D1 is connected with X dash Y. So this is X dash and this is Y. And D0 is connected with X dash Y dash. X dash Y dash. This is X dash and this is Y dash. Like this. So this will be the inside the decoder. Inside the decoder. What is the inside decoder? AND gate. AND gate, and you can also say NOT gate. Clear this thing? Now, so if you will represent in this way, this is the decoder circuit, and here this is 2 input, this is 0, this is 1, this is X and this is Y, and this is your enable signal. Here 1, 2, 3 and 4 output, D3, D2, D1 and D0, like this. So this circuit, inside this circuit is nothing but this logic gate. Okay. Now if I am going to draw Suppose here enable bar, suppose for example, then what will be changed in this circuit? Nothing will change, only you have to put here one NOT gate, only this thing, nothing will change. Clear this thing? So this circuit is active high decoder. You can write here, this circuit is active high decoder, active high decoder, active high decoder. Okay, just complete this. This is nothing but a active high decoder. Now I am going to consider, okay, one doubt you have, okay, just you should consider this. Wait some time, all the doubt will be clear. Okay, now you have asked me, sir, two types I have studied. Yes, active low enable, which only enable is low and output is active high only. Other type, when output is active low, not depend on enable. So sir, active low input. No, just wait. What is the active low decoder? Just wait. Okay, I am going to consider what is the actual active low decoder, what will be truth table, and what will be the inside of the circuit, and then I will ask you which one is better, active low decoder is better or active high decoder is better. So I hope ki now active high decoder is clear to all of you. Okay, now I am going to consider active low decoder. Now I am going to consider active low decoder. Always I suggest you, always you have to follow good books. If anybody want digital books for any suggestions, so I recommended for the theory part, you can follow this book. You can follow this book for the digital circuit, Tochi and Widmer. That is a scientist, that is a writer name. Just you can find out Tocci. Okay, Tochi. So if anybody want to study from the books anytime, you can always follow this book. This is the best book. Okay, in MIT, Oxford, Stanford, many US institutes and Europe institute will follow these books. Okay, now our next target is active low decoder. Active low decoder. Why active low decoder is required? Why? The reason generally we implement any circuit by NAND gate. Definitely. Now, so if I want to change this NAND gate, this NAND gate, this NAND gate, and this NAND gate, nothing else. This circuit is a active low decoder. Nothing change, only if I will put here NOT gate, means if I will change this AND gate to NAND gate, then this circuit is called active low decoder. This circuit is called active low decoder. Then how we can represent active low decoder like this? How we can represent active low decoder? Suppose this is 0 and this is 1, this is X and this is Y. Here enable can be anything. But generally active low enable, generally we will use active low enable generally. That's why generally you can write here bubble, but that is not for active low or active high. That is the standard things. So this signal you will receive from the microprocessor, and generally microprocessor provided us a active low enable signal. So most of the time this is active low signal. So this you can also use here either active low or active high, that is your choice. Okay, and that is examiner choice. So suppose I can consider here E bar and I can also consider here E. I can consider anything. Only this NOT gate will be different for the active low enable and active high enable. Clear? But inside what change you have done here, you have put here some bubble. So active low decoder we can represent in this way like this. So this is nothing but D0, this is nothing but D1, this is nothing but D2, and this is nothing but D3. So for the active low, you don't write this is D0 bar. You don't write. This signal is D0, this is D1, this is D2, and this is D3. But what will be the inside here? Inside here this is NAND gate, and in active high, inside this is AND gate. This is the difference. This is the only difference. In active high decoder, inside decoder is AND gate, and in active low, inside the decoder is NAND gate. So how you can differentiate active low and active high? How you can differentiate? So we have two choices. Either examiner will write that is active low decoder, or examiner will provide you here bubble. Either examiner will write active low decoder or examiner will provide you here bubble. By using this only we should know the decoder is active high or active low. Now I hope you can differentiate. Now what can be the truth table? What can be truth table? Okay, now this is the enable signal. This is the enable signal. Input is X and Y. Input is X and Y, and output can be your again D3, D2, D1 and D0. Okay, now if enable is 0, because I am considered here active low. So enable is 0, if this is 0, 0, enable is 0, this is 0, 1, enable is 0, this is 1, 0, and enable is 0, this is 1, 1. Again I am saying, don't say if enable is 0 active low, enable is 1 active high. No, that is totally wrong. Clear? Enable can be anything in any cases. But generally we follow active low enable because microprocessor generally provide us active low enable signal. Clear this thing? This was the reason. So if XY00, which output you will get, I will receive D0. I will receive D0. But D0 in the form of disable. LED will be off. Remaining LED will be on. So if you have 4 LED in decoder, 1 LED is off, 3 LED is on. Means what is the output? Which LED is off? And if 1 LED is on, 3 LED is off, means which one is the output? The LED which is on. So that is different. Out of 4 or out of 8 or out of 16, the one LED will be either on or off, remaining LED will be in another stage. That one single LED is your output. That can be either on or that can be either of your two choices. So here this is an active low decoder and output is D0 and this output is treated by 0. Remaining LED will be represented by 1, 1 and 1. Now here this will be 0 and this will be 1. Here this will be 0 and this will be 1. And here this will be 0 and this remaining will be 1. Clear this thing? So this is the difference between active low and active high. This is nothing but 2 cross 4 and this is active low decoder. This is active low decoder. This is active low decoder. Clear? This is active low decoder. And what will be the last case? When enable is 1, input can be anything. What will be in this case? All the LED will be on. All the LED will be 1. This is 1, this is 1, this is 1 and this is 1. Because in previous cases, if enable was not enable, then all the output was 0 and now 0 bar will be 1, 1, 1, 1. This is the second advantage here for the active low. At high impedance state, all the LED is on. In railway station, sometime you will see in the display board, if your coach number are exactly not displaying by the your station master or anybody, then sometime that is blank, Then what do you think? Either they have not provided the output or the LED is, you can say that is faulty, But if all the LED will be blank means all the LED will be on, but coach number are not displaying, then what you feel? Yes, the device is in working condition, they have not provided the output. So active low will be better with respect to active high. Two terms. First thing, in high impedance state, at least you should get, yes, device is working properly because this all the LED will be on. This is the first condition. Second condition, inside the active low decoder, you will get a NAND gate, and always we design any circuit by NAND gate. Clear this thing? So active low is better than active high decoder always. Okay. So this is nothing but high impedance state. High impedance state. You should be more comfortable in active low and active high. Clear? Now just you can note down this. Here we considered enable bar. When enable bar means 0, then this will be on. So you can write here You can write here one NOT gate. Just note down this circuit for the active low. So can I write here active low decoder? So this circuit will be for active low decoder. Clear this thing? So this is the representation of active low. Either examiner will provide you here bubble or examiner will write active low decoder. This will be the truth table and this will be the circuit. Clear? This will be the circuit. Anybody can say? Now anybody can say what you feel. Active low is better or active high is better? Tell me your answer. What you realize? Which one is better? Which one is better? Active low or active high? Okay, you have to complete this. Na? Active low are better or active high are better? I hope now this differentiation is clear between active low and active high. Okay, tell me your answer. What you think? Which one is better? Active low is better or active high is better? Okay, now my next target, implement any boolean function. Implement what is the use of decoder? If somebody will ask you what is the use of decoder? What is the use of decoder? So decoder can be used at many places. At many places. Decoder can be used to represent address lines. First thing. So in every memory, decoder will be present before the memory. Before the memory, always decoder is present. Just you should remember my words. In every memory, decoder will be present before the memory, always. Because in memory, there are so many number of address lines. There are so many number of address lines, and decoder, you can say there are so many number of addresses. There are so many number of addresses. Suppose for example, I am considering total addresses 16. Suppose, clear this thing? Now, what is the use of decoder? So mainly in digital circuit, at two places we will use decoder. First place before the memory. How before the memory? Suppose for example, we have 16 address 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. Suppose we have 16 address. Okay, I am going to write 0, 1, 2, 3, 4, 5 till 15. Total we have 16 address. Then how many person is required to locate this address? So somebody will take 16 person. No, 16 person is not required. I will put here one decoder. Then decoder will have 16 lines. And decoder will have 16 lines like this. So this is required 4 cross 16 decoder. And here only 4 input is required. This is, you can say 4 input. Clear? So by using 4 input, you can locate 16 address. In one time, you have to reach at one address only. So by using this decoder, this is nothing but a 4 cross 16 decoder. This is the first use of decoder. So before every memory, decoder are present. Clear? Now, what is the main application of decoder? What is the main application of decoder? Main application, we can implement any boolean function by decoder. We can implement any boolean function by decoder. This is the important thing. Now, which boolean function you want to implement? Now I want to implement adder circuit by using decoder. Now I want to implement adder circuit by using decoder. Okay, adder circuit by using decoder. Now, so first question, implement half adder by active high decoder. We have to implement half adder by active high decoder. How you can implement? Suppose you have to implement x XOR y and x dot y, sum and carry. How many input is required? 2 input is required. This is 0, 1 and this is XY. Enable you can assume anything either by active low or by active high. Now I am considering by active high. You can consider this anything. Now here 2 output. This is 0, this is 1, this is 2 and this is 3. What do you mean by 0? 0 is nothing but X dash Y dash. 1 is nothing but X dash Y. 2 is nothing but X Y dash and 3 is nothing but X, this is X Y dash and this is X Y in active high. And now you have to implement half adder sum. Half adder sum is nothing but X XOR Y means mean terms of 1 and 2. So you have to put here one OR gate and this is connected with 1 and 2. What output you will get here? X XOR Y, or you can say mean term of 1 and 2. And this is nothing but sum. This is nothing but a sum. What will be the carry? Carry will be X dot Y, mean directly this. This is nothing but carry. This is nothing but carry. And what is the function? X dot Y. X dot Y. And what is the mean term? Mean term, and that is nothing but 3. So by using decoder and OR gate. So by using decoder plus OR gate is equal to any boolean function. Is equal to any boolean function. Which decoder you have considered here? Active high. So I am going to write here active high. Clear? Now if I will ask you what will be the inside of active high? So inside of active high decoder is nothing but AND gate. So this circuit is nothing but AND gate and this is nothing but OR gate. And you know very well any boolean function is generally represented by SOP, and we have two choices for the SOP, AND or NAND. So this is nothing but by using AND or you can get SOP. You can get SOP. Clear thing? So what designer have think here? They have implement AND array, and OR array is the outside. So this inside is the AND array and outside is the OR array, and any AND array or array will provide you any SOP function. Now my next question. Implement full adder. By active high decoder. Now my next question. Implement full adder by active high decoder. Then I will also consider same question for the active low. Okay, so first we have to design this circuit full adder by decoder circuit. So first you should know the function sum. Sum you can represent, suppose sum is nothing but a comma b comma c in is equal to, what is the mean term? Mean term is nothing but 1, 2, 4, 7. You should know the mean term. And now what is the carry? Carry, and this is nothing but a comma b comma c in, and this is, you can say, carry out. You can also say this is C out. Okay, is nothing but 3, 5, 6 and 7. 3, 5, 6 and 7. Clear this thing? 3, 5, 6 and you should remember this. In previous classes already I tell you, if you forgot this 3, 5, 6, 7, just remember the majority gate. In 0, 0, 0, 0 is the majority, 0, 0, 1, again 0 is the majority, 0, 1, 0, again 0 is the majority, but 0, 1, 1, 3. So first term is 3, and in 4, 1, 0, 0, again 0 majority, in 5, 1, 0, 1. So 5, 6, 1, 1, 0, 2, 1 and 7, 3, 1. So 3, 5, 6, 7, you will get 2 number of ones and 3 number of ones. So by majority input, you can remember this thing if you forgot. Okay. Now, how to implement this circuit? You have to consider what is the size of decoder required. 3 cross 8 decoder is required, because how many total mean term is required? 8. So here, what is the decoder size is 3 cross 8 decoder. Clear this thing? How many input here? 1, 2, 3. This is 2. This is 1. This is 0. This is A. This is B and this is C in. And here you can consider enable either active low or active high. Now I am considering here active low. Active low enable. You can consider anything. Then how many output here? 8 output. 1, 2, 3, 4, 5, 6, 7 and 8. I can consider this as 0, 1, 2, 3, 4, 5, 6 and 7. Clear this thing? Now you have to implement two boolean function. Two boolean function, then how many OR gate is required? How many OR gate is required? Two OR gate is required. How many OR gate is required here? Two OR gate is required. So this is the first OR gate and this is the second OR gate, and this is nothing but sum and this is nothing but C out. What function is required here? This is nothing but mean term of 1, 2, 4, 7 and this is nothing but mean term of 3, 5, 6, 7. Now just you have to connect. You have to connect this with 1, 1 and this is 2 and this is 4 and this is 7. Just you have to connect with like this 1, 2, 4, 7. Now the next you have to connect 3, 5, 6, 7. So here this is 3, here this is 5 and here this is 6 and here this is 7. This will be the full adder. Now you don't have to design full adder separately. You can implement full adder by decoder circuit. Clear this thing? Now what will be inside of this decoder is AND array. Can I say? This is nothing but AND array. And what will be the outside of the decoder? This is nothing but OR array. So AND array plus OR array is nothing but SOP. So this is nothing but AND array plus OR array is equal to SOP, sum of products. So you have two choices of SOP. Why we are going to prefer SOP? In previous classes already I tell you, SOP is always preferred over the POS. That's why we are not going here for the POS. We are only targeting SOP. Clear? Now we have two choices for the SOP. First choice is AND array OR array. Second choice is NAND array plus NAND array. You have two choices. Or the SOP. Which choice is better? Always we prefer this second choice. This is implemented by NAND and NAND. So active high is not very much useful for us. Active low will be very much useful for us. What will be inside the active low? You know very well, that is NAND gate. What will be the outside of? What should be the outside of active low? That is nothing but NAND gate. So what we can do here? Here can I change only? Can I put here two bubble? And can I put here bubble? And can I put one more bubble? So here can I put one more bubble? Clear this thing? Now what will be this circuit? This is nothing but active low decoder. And what will be this? Bubble OR gate. And bubble OR gate is, what is the bubble OR gate? This is bubble OR gate. And what is the bubble OR gate? NAND gate. This is bubbled OR gate. And bubble OR is called NAND gate. This is nothing but NAND. So what will be the inside of active low? Already we studied. What should be the outside of this? This is nothing but NAND gate. Clear? So now my next target is implement full adder by active low decoder. So just change the question. Implement full adder by active low decoder. Clear? Now I am going to draw the circuit. This theory is very much important. In whole combinational circuit, everything is this two. AND OR or NAND NAND. Because we have two methods to implement any SOP. Clear this thing? We have two methods to implement any SOP. Now you can think only like this in whole combinational circuit. Now we have to implement full adder by active low decoder. How you can implement? Now you know very well. First active low decoder, 3 cross 8. How many input? 1, 2 and 3. This is 2, this is 1, this is 0. This is, sorry, A, B and C in. This is A, this is B and this is C in. This is suppose 0, 1, 2, 3, 4, 5, 6, 7. Okay, now here you can write bubble. This is bubble, 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 this is. Suppose if you want to write this function, what will be this function? You can say this is a D0. What will be the D0 for active low? For the active low, you will write this A bar, B bar, C in bar, whole bar. You can write whole bar with respect to active high. And you can also say this is nothing but A plus B plus C in. You can also say this is nothing but A plus B plus C in. Clear this thing? Suppose if this thing is required, you can write in this way. Theory should be very clear. You can think always here, this data is A bar, B bar, C bar. And what will be here? A bar, B bar, C bar, whole bar. Clear this thing? Now you have to implement 1, 2, 4, 7. For active low, directly you can design here or consider here NAND gate. Why you are considering NAND? You know very well. This is NAND and this is NAND. So NAND and NAND will become AND OR circuit, or you can say SOP. Already I tell you why you are considering here NAND. Because you have to first cancel this bubble. You have to cancel this bubble and you have to add. Then you have to put here bubble OR gate. And bubble OR gate is replaced by easily NAND gate. So directly you can connect here 1, 2, 4 and 7. 4 and 7. Okay, so here you have two choices, either bubble OR gate or NAND gate. So we will consider NAND gate. We don't consider bubble gate. Okay, like this. This is carry. Carry is nothing but 3, 5, 6, 7. This is 3 and this is 5 and this is 6 and this is 7. This output is nothing but sum and this is nothing but C out. Clear? This is nothing but C out. Now, what enable signal you can consider? I am considering active low. That is your choice. You can consider active high or active low. So we have to design to implement any boolean function. Any boolean function is generally represented by SOP. In gate exam, they can ask you anything. But in the real life, always decoder, we have two kind of decoder, AND OR circuit and NAND circuit. We don't design decoder for the POS. Clear this thing? Okay, so from the POS they can ask you basic questions, but in decoder circuit always we will implement SOP function. But we have two choices for the SOP, AND OR circuit and NAND circuit. Clear? Okay, so we will prefer always active low decoder because here easily you can implement by NAND. So if I will ask what will be the inside of whole circuit, only NAND gate. Inside, if you will click, suppose you are going to design this circuit in computer. If you will go with double click inside of this decoder, you will see only NAND gate, and here you have to connect only NAND gate. Clear this thing? So by NAND circuit you can implement any boolean function. This is the digital. Now you are not going to implement full adder by connecting gate, logic gate. No. Just you will purchase a decoder circuit from the market and just you will connect here NAND gate. Clear this thing? Now if I will ask what is the drawback of this decoder circuit or what is the disadvantage of this decoder circuit? What is the disadvantage? Extra logic gate you have to connect. So can I say disadvantage? Extra logic gate is required. Extra logic gate is required. Okay, to implement any boolean function. So at least you have to connect this logic gate with decoder circuit. What is the advantage? By using one decoder, you can implement many number of boolean function. By using this one decoder, if I will ask you implement adder cum subtractor circuit, so you will also consider here one more NAND gate. This is for the adder and you can say this is sum or difference. Can I say this is sum or difference? And this is carry out. You can also consider here one NAND gate and this is nothing but borrow. and you can connect this borrow min term with 0 to 7. So by this is the advantage of decoder circuit. What is the advantage? So by using one decoder circuit, one decoder we can implement many boolean function simultaneously. So in one time you can implement many number of boolean function by using one decoder. So can I say one decoder is equal to how many boolean function you can implement? Many boolean function we can implement. This is the advantage. Many boolean function. Clear the thing? This is the advantage. Now adder cum subtractor circuit easily you can implement by this decoder. Clear the thing? I hope everything is clear. Now I hope everything is clear. Okay. If anybody have any doubt, just ask me. Now I am going with the real design. Do not worry, in GATE you can solve any question. Now written question I will ask you. Now in GATE exam, what I will ask you question here? What is the GATE level question here from the decoder? Clear this thing? Now I hope active high, active low, why you are studying this decoder? What is the advantage of decoder? You can implement any boolean function. What is the disadvantage with decoder? Now you should be very comfortable. Now if I will ask a reverse question, in GATE exam, which kind of question they will ask you? In GATE exam, which kind of question they will ask you from the decoder? Like this. They can ask you this circuit. And they will ask you, suppose this function is P. And this function is Q. How to solve this kind of question? Either this bubble and you can put here one bubble, or you can replace first this circuit by like this bubble OR, and now you can also replace all the bubble. If you don't know directly, that is active low process. If you know directly, you can write P min terms of which this is connected 1, 2, 4 and 7. So directly you can write P is nothing but 1, 2, 4, 7. And now you can write the boolean function. But suppose if you are not comfortable in this, what you will do? First you will convert this NAND gate to bubble OR. Then every bubble you have to cancel. This will be OR gate and all this bubble will be cancelled. And now you can say this is min term. And already we have studied how to process min term with any logic gate. You are expert in that part. So here you will get min term. And any min term you can process by any logic gate. Examiner can also provide you here different logic gate. Suppose examiner are providing this circuit. Suppose like this. This circuit examiner are providing you. What can be the answer? What you will write? So this is connected with min term 1, 2, 4, 7. So what will be the P? P is nothing but here you will get min term 1, 2, 4, 7. Clear? Then after bar what you will get? Max term 1, 2, 4, 7 or 1, 2, 4, 7 bar. Then what you will get? This function P. This P you will get min term 1, 2, 4, 7 whole bar. Then what you will write? 0, 3, 5, 6. This will be the answer. So they can ask you anything here. Clear this thing? They can ask you anything here. Okay, one question I am going to ask you and you have to give me the answer. Okay, one question I am going to ask you. So here one question I am going to ask you. Okay, now let's see. Suppose this question, suppose like this. This is X and this is Y. This is 0, this is 1, means MSB is X. And now this is enable signal, this is enable. Okay, now here this is 0, this is 1, this is 2 and this is 3. Like this. Okay, and now here 1 XNOR gate is given like this. And this is connected with 1, this is connected with 1 and 2. like this. And here also I am considering one AND gate, and this is connected with 2 and 3, and this function is P, this is Q. What is the variable X and Y? P X Y is equal to Q X Y is equal to question mark. Anything they can ask you, examiner can ask you anything, how to solve. So directly you can write what is this mean term, X dash Y dash, what is this X dash Y, what is this X Y dash, and what is this X Y. Now you can process. What will be this? What will be this? So you can write this is nothing but X dash Y XOR gate X Y dash, and now you can process. Also you can use here K-map. Also you can use here K-map. You can also write this is mean term of 1 and this is mean term of 2, and mean term of 1 and 2 you should pass from the XNOR gate, from the XNOR gate. And you are already expert in this. Already I tell you what is the XOR output, how you can process. Here 1 are present and here you can see 1 are present or not. Or you can find out this complement. Yes, if you will find out this complement, 1 will be present and here 2 is present and here 2 is not present. Then what will be this output? This before NOT gate, mean term of 1, 2. Then what will be the final output? So this answer directly can I write, this is nothing but mean term of 0, 3. If you will solve, you will get this answer. Try to solve. Already we studied how to process mean term by any logic gate. And here what you will get? This is nothing but mean term 2, mean term 3. And this is 2 and 3. Which term is the common? So here you will get nothing. You will here get everything is 0. Nothing you will get. Here mean term 2, mean term 3, mean term 2 and 3. If you will pass from the AND gate, you will get nothing. Then you will get everything here. Then what will be the answer here? 1. Or you can also write this is nothing but mean term of 0, 1, 2, 3. And 0, 1, 2, 3 is the answer 1. Is the answer 1. Clear? You will get this answer. So 1, 0 and 3 what you will write? This is nothing but XY plus X dash Y dash. Can I write? And here you will get answer is 1. Answer is 1. If you will put 0, 1, 2, 3 over the K-map, you will get 1. This thing you should remember. This thing you should remember. If all the cells having 1, then output result is 1. And if all the cells having 0, then result is 0. So here this is X, this is Y, this is 0, 1, 0, 1. It means you will make this group. And this answer is 1. If all the 1s are 0, then result is 0. This thing you should know. So here all the min terms are present, means result is 1. Clear? Now you can also find out. Clear this thing how to process? Now one more question I am considering. Here. Next example. Suppose for example this decoder is given. Suppose for example this decoder is given. This is XY and this is 0, 1. And this is active low. This is active low. This is 0, this is 1, this is 2 and this is 3. Then what will be here? Min term of 0. Then what will be the bubble? Max term of 0. Or you can say min term of 1, 2, 3. So here output you will get min term of 1, 2, 3, min term of here 0, 2, 3 and here min terms of 0, 1, 2. So you have to process by bubble gate as well as by the min terms. Okay, suppose this question is given and here this is enable signal and I have considered here in previous case enable is 1. Clear? And here again I am considering enable is 1. Then examiner will ask you the output. Okay, now in this case suppose if I will put here one NOR gate and this NOR gate is connected to suppose for example 1 and 2. This NOR gate is connected to 1 and 2. One more gate I am considering here NAND gate. And this NAND gate is connected to suppose for example 1 and 3. What will be the output? And this is P and this is Q. What will be P and Q? How to process? You should try to cancel this bubble first. How you can cancel? This gate is converted. Or you can collect this bubble. And you can put here. Can you cancel this bubble? Can I write in this way? Yes. Can you cancel this bubble also? This bubble you can put here, and this bubble you can also put here, and this is not connected to anyone. Now you can process. This is nothing but you can convert this gate. This is bubble NOR. Bubble NOR is nothing but AND gate. So this is nothing but AND gate. And this is again bubble NAND. Bubble NAND. Bubble NAND gate is nothing but OR gate. So this is AND gate and this is OR gate. Now what will be the P? P is nothing but 1 and 2 mean term. 1 and 2 mean term AND. You will get nothing. So this P answer will be 0. P answer will be 0. And here this is OR gate. And this is connected with mean term 1 and 3. Then what answer you will get? Mean term 1 and 3. And 1 and 3 you can write. What you can write? 1 means 0, 1. 0, 1 means x dash y. Plus 3 means xy. xy. What you can write? If you will consider y common, x plus x dash is 1, answer is y. This will be the answer. This will be the answer. Now you have to solve like this. You should be expert in logic gate. You should be expert in bubble. Already we studied, and I hope ki now we are expert in this processing of bubble gate as well as processing of any mean term by any logic gate. Already we are expert in this part. Already we studied in our previous lectures. Can you solve any question? You can solve any question, any question. You don't have to practice many number of questions here. Now you can solve anything. You can solve anything. Clear this thing? Now you can solve anything here. If anybody have any doubt, just ask me. If anybody have any doubt, just ask me. Yeah, please always you have to respond me. Always you have to respond me. If you will respond, definitely you will get many new things also. Please always respond me. Clear this thing? So can you implement any boolean function by using decoder? Active low and active high, that is very important. But in gate exam, they will ask you reverse question. They will ask you any kind of circuit. They will provide you any kind of circuit and they will ask you what will be the output. What will be the output of this circuit? Clear this thing? What will be the output of this circuit? Okay, they can provide you active low or active high. What you have to do? Always you have to cancel this bubble for the active low. That will be easier for you. So if an active low gate is given, just you have to remove bubble from here and you have to put that bubble over the logic gate. And now you are very much expert in the bubble gates. I hope you are expert in the bubble gate. Okay, now the next. Now what is the modified version? Now I am going to consider modified version of decoder. Modified version of decoder. Okay, now modified version of decoder. Anybody can say what is the modified version of decoder? Anybody can say me? Modified version of decoder. What is the modified version of decoder? The name of that circuit. Now my next target. Why modification is required? Why modification is required? Because in decoder circuit, one disadvantage. There are one disadvantage. What disadvantage? Extra logic gate we have to connect. Means again you have to soldering or you have to connect like this. Now our next topic from here, modified version of decoder. Which circuit is a modified version of decoder? That circuit is called ROM. And this is also you can say PROM. This is not a memory. This is one again structure. That is the structure. You don't say ROM. Yeah, name of ROM is read only memory, but that is a one digital structure. And what is the use of this ROM or PROM? What is the use of this ROM or PROM? What is the use of this ROM or PROM? To implement any boolean function. Again, to implement any boolean function. Again, how? This is nothing but modified version of ROM. Now, suppose I am considering here 2 cross 4 decoder. 2 cross 4 decoder. This is nothing but 1 and this is 0. This is x and this is y. Here 4 output 1, 2, 3 and 4. I am considering active high. You can also consider active low. Okay, suppose this is 0, this is 1, this is 2 and this is 3. So you have 4 output. What is this 0, what is this 1, what is this 2 and what is this 3? 0 means x dash y dash, 1 means x dash y, 2 means x y dash and 3 means x y. Now if you want to implement XOR gate and XNOR gate, what is what we have to implement here? Two target. P is equal to X XOR Y and Q is equal to X XOR Y. So we have to implement here two logic gate. Which logic gate? Okay, Q I am considering X dot Y. So we have to implement here two logic. Okay, we are considering suppose X XOR Y. Okay. So we have to implement P XOR Y, sorry, X XOR Y P and X XOR Y Q. How to implement? So in ROM circuit, we don't have to connect extra logic gate. The extra logic gate are already present inside the circuit, already present. So here two OR gate was present like this. Here two OR gate was present like this, and this is P and this is Q. Like this here, and here this is 4 outputs, so here 4 input gate, this is 4 input gate and this is 4 input gate like this, and here this is connected from here, connected from here and this is connected from here like this. Clear? Now again this is connected from here, this is connected here and this is connected here and this is connected here like this. Clear this thing? Now here one fuse wire are connected, one fuse wire are connected like this. These if you will say this box, you can also consider here enable signal. Okay, now like this. This box is called ROM circuit. This box is called, either you can say ROM or you can say PROM. So in decoder circuit, this extra gate you have to connect. But in ROM circuit, already this OR gate, if you will consider this active low, suppose if you will consider active low, so you have to consider here NAND gate only. But that will be the inside of the ROM circuit. So two cases can be possible, either active high decoder with a programmable OR gate or active low decoder with here programmable NAND gate. So two choices can be possible. We don't know what is the inside of this ROM. That will depend on the designer. Okay, now what is our concentration? Suppose if you want to implement this P is equal to X XOR Y, and if you want to implement Q X XOR Y, it means X XOR Y means min term 1 and 2 and X XOR Y means min term 0 and 3. Then what you will do? These are nothing but fused wire. This was nothing but fused wire. Then what you have to do? You have to here, you will connect 1 and 3 and you will disconnect this 2. Again here you will connect this 0 and 3 and you will disconnect this 2. Clear? How we can connect or disconnect? How we can connect or disconnect these switches? So different types of switch are available in today's world. Okay, so in today's world, this switch are, so in previous I write here fused switch. Now this switch is converted into, so if you are considering fuse wire or you can say fuse switch, this is nothing but ROM. Now if you will use in place of this fused wire programmable switch, so if this switch is suppose programmable switch, then you can say this circuit is PROM, programmable ROM. Then you can say PROM like this. Now we have to study actual PROM, and this is very important topic. Generally in GATE you will get question from this PROM. Now how we can represent PROM? Just wait. How we can represent PROM? Clear this thing? So here in ROM circuit is nothing but in ROM circuit already one decoder are present, means AND array are present, and here OR array are present. You don't have to connect extra logic gate. But what is the limitation of this ROM? Here if you are going to purchase a ROM for 2 output, then you cannot implement 3 output. If you are going to purchase for the 3 output, then you cannot implement 4 output. So here output is fixed. You cannot modify here output. Clear this thing? So this thing is called here M, and this input is called N. What is the ROM size? So just you should note down what is the size of ROM. ROM size we can say 2 raised to power n cross m. What is the n? N is equal to number of input. And what is the m? M is nothing but number of output. And number of output means number of boolean function. And this is nothing but number of boolean function. Number of boolean function. So we have only one limitation of the ROM. What limitation? Number of output is fixed. Can I say one more thing? Anything relation between n and m? No, there can be n and m. We don't have any relation. So here n and m both are separate. Both are. Can I write? Separate. N and m don't have any relation. N and m don't have any relation. N can be anything and m can be anything. Clear this thing? N can be anything and m can be anything. Now I am moving towards the gate level question and PROM. This circuit is actual for the ROM. In ROM, we will use here fused wire, and a fused wire, okay, in initial when you will purchase, all the wires will be connect. All the wires will be connect. Only you will disconnect which you don't want. Which you don't want, you have to disconnect. You have to disconnect. Means just you have to fuse the wire. You have to fuse the wire only. If one time you will fuse the wire, then this modification is again not possible. Again modification is not possible. You can treat this like as a CD drive. If you will write any data in CD drive, again you don't have to change anything. But if you will purchase programmable, rewritable CD or DVDs or Blu-ray, read writable, then you can read, again you can erase, then again you can write, you can do anything. You can write, erase, read, anything. But so this is nothing but, that's why we call this is ROM. If you studied in memory ROM, what is the ROM? In ROM, that is not a programmable. Only you can read the data. Only you can read the data. So here only one time you can design this circuit, and next only you can use this circuit. But what is your actual requirement? Our actual requirement is the PROM. So this switch should be programmable, and what we want we can change. We can alter the switch on or off. Clear? So this switch is replaced by the programmable switch, and in GATE exam you will get question from this programmable switch. In GATE exam you will get question from this programmable switch, and this is very easier topic. Very easier topic. So first you should know here what generally student will face problem. Student face problem. Student don't judge exactly from which topic they have asked the question. Only this thing, if you will concentrate, this is a question from the PROM, then within 30-40 seconds you can solve any problem. Now same circuit if I want to implement by PROM, same circuit if I want to implement by PROM, then what you will use like this. This is again 2 cross 4, and this is x and y. This is 0, this is 1, this is x and y. How many output? 4 output. 1, 2, 3 and 4. This is 0, this is 1, this is 2 and this is 3. Two function we have to implement, P and Q. So just you have to write here P and one line, and we can also draw here one line, and this is Q. And here we can write this is programmable switch, programmable switch, programmable switch and programmable switch. Here this is programmable switch, programmable switch, programmable switch and programmable switch. Clear this thing? Now if you want this P is equal to x XOR y, means which min term 1 and 3, then this will be disabled. This switch is not connected and this switch is not connected. There, if you want this Q function is equal to x XOR y, means min term 1 and 3, then this switch will be connected and this switch will be not connected. So this is not connected and this is not connected, like this. So this cross will indicate that is a connected. So here P, how you can write this plus this P exactly, you can treat here, use as a virtual OR gate. This is nothing but OR, like this. So this P function is nothing but a mean term of 1 and 2. So what you will write here P? P is nothing but mean term of 1 and 2. And what is the Q here? Mean term of 0 and 3. Clear this thing? So this kind of question in GATE exam you will get. So first you should know this is nothing but PROM structure. And what is the PROM structure? This function where this is connected, all the mean term will be added. All the mean term will be added. And here this and this mean term will be added. Clear? And what you can say, this is nothing but a programmable switch. Programmable switch. Programmable switch. So everywhere, here, 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 here and here, here, in all the connection, programmable switches are present. Programmable switches are present. Only what you will do connect or disconnect. So what we have done here, disconnect, here connect and here disconnect by using programming. Now you can use this circuit many times for the many boolean function. This is the best structure in today's world. We will use this structure in real life also. So in real life, many digital circuit designed by this structure. What is the advantage of this structure? The main advantage of this structure, you can implement many number of boolean functions simultaneously by using one circuit. By using one circuit. Clear this thing? By using one circuit. This is the advantage with a PROM structure. Clear this thing? Now, here different kinds of question examiner can ask you. Here different representation can be possible. Here different representation can be possible. Okay. Now, I am considering the next example. Here, how examiner can also represent this circuit in this way. Examiner can also provide you in this way. This is X and Y, this is 0 and 1. Here this is 0, 1, 2, 3, 4 output. This is 0, this is 1, this is 2 and this is 3. Now again, suppose this function is P and this function is Q. So two output are possible here. Now examiner can also provide you like this. Here they can provide you like this. Clear? It means this 1 are connected to output and this 2 are connected to output like this. And similarly, examiner can also provide you in this way like this. This is 0 and this is 3 like this. So different representation can be possible because this is a switch and you can implement switch by different circuits. By diode you can also make a switch. Many number of switches you can design by the different ways. Clear? So this is the standard representation, but in GATE exam this is latest GATE, just current year GATE question. What will be the output? If examiner will ask you this question, what will be the output? This circuit is nothing but 2 cross 4 decoder and they have provided, suppose this is enable bar and this is enable bar is equal to 0. If this is 0, this will be enable. Now what will be the function P? What you will write? P is nothing but P is connected to 1 and 2. Then what you will write? Mean term of 1, 2. And mean term of 1, 2 is nothing but X, X or Y. What is the key? Q. Q is nothing but mean term of 0 and 3. And this 0 and 3 is nothing but X, X nor Y or X, X or Y whole bar. This is the answer. Yeah, the examiner can also provide you here in matrix form. They can also provide you in the matrix form. Okay, so different representation can be possible here. Different representation can be possible here. Clear? Suppose if I will write this line are A in terms of AB. So what examiner can provide you? This switch number, suppose D00. Can I provide? If I want to write down this thing in the matrix form, then what I will say? Suppose this is 0 and this is 1. Suppose just I am providing you the name. What will be this name? 00. What will be this name? 01. What will be this switch name? 10. This switch name 11. What will be this switch name? 21. Sorry, 20. What will be this switch name? 21. What will be this switch name? 30. What will be this switch name? 31. So they can provide you anything. And now you can draw in the matrix form. Suppose if I want to draw this switch in the matrix form. What I can write? This first one is the 00. Second one is the 01. Like this. Next what you can write? Next one will be the 1 0 and next one will be the 1 1 and this is 2 0 and this is 2 1, this is 3 0 and this is 3 1. Can I write? You can also write D0 0, D0 1, D1 0, D1 1 like this. This is the switch representation. This is the switch representation. You can represent switch by like this matrix form. And the which switch is connected, you can say that switch is the 1 and which is not connected, that is 0. Then how you can represent? How you can represent? If any switch is connected means 1 and not connected means 0, then what you can write? This is not connected, this is connected. You can write this is 0, this is 1. And here you can write this is connected, this is not connected. This is 1, this is 0. This is connected, this is not connected. This is 1, this is 0. This is not connected, this is connected, this is 0, this. Like this. Different kind of question examiner can ask you. This is just latest year gate question. Many students are stuck in this. Many students are stuck in this. So now I hope ki in this PROM you will get lots of different varieties of question. These are the gate question. These are the gate question. This matrix representation are the also a previous year gate question. Now I hope you are comfortable in. Now I hope you are comfortable in decoder circuit. Decoder circuit, and also you are comfortable in what is the ROM and what is the PROM. If somebody will ask you what is the advantage of decoder, what is the disadvantage of decoder, you can tell. Now what is the advantage with ROM or PROM, you can also say. So this is nothing but just modified version of the decoder circuit. Okay, so decoder have two basic use. First use, before memory to represent all the address. Decoder is always used. In that place you cannot use PROM. And if you want to implement any boolean function, then generally we use modified version of the decoder, and the name of that circuit is called PROM. But here programming is required. If you don't want to do programming, one fixed circuit if you want, we can use here ROM. If you want one fixed circuit, we can use ROM. But if you want to modify always, we can use PROM. So for PROM you have to do programming. By programming you can connect or disconnect to any switch. By programming or outside you can design one box. Clear this thing? I hope now this thing is clear to all of you. Now I am considering one question from this topic. Clear? And you have to try to, and you have to solve and give me the answer. Okay, now clear this? Okay, now from this PROM, I am going to ask you one question. From this PROM, I am going to ask you one question. Okay, just note down one problem. Okay, now suppose I am considering 3 cross 8 decoder. This is 3 cross 8. This is 0, 1, 2, 3, 4, 5, 6 and 7. And here this is 3 input. This is 0, this is 1, this is 2, this is X, this is Y, this is Z. This is the 3 input. And here 8 outputs are present like this. And we are going to implement here 2 functions. This is the first function, and this first function is f1 and variable is x, y, z. And this is the second function f2 and variable is x, y, z. 2 functions you have to implement. First function is connected to, this is 1, this is 2, and this is 4, and this is 7. And second function is connected to 3, 5, 6 and 7. What you can call? What is the first function? First function f1 x, y, z is nothing but mean term of. If examiner will not provide you here any gates, so you have to understood if this is a active high, so this will be OR gate. If this is active low, this will be NAND gate. Clear this thing? If examiner will not provide you, but if examiner will provide you, suppose here NAND gate and this is active high. Suppose, then you have to try to solve in this way. Then this mean term will pass from the NAND gate. Clear this thing? But don't worry, generally examiner will not provide you in this way. If this is active high, here OR gate, and if this is active low, here NAND gate. Okay, suppose if I will provide you here, just change the question. You should change the question in this way. Suppose this is active low, then here this is nothing but practically NAND gate, and here this is nothing but practically NAND gate. It means This NAND, that is nothing but NAND and NET is converted into AND OR. So directly you can write. So just note down this problem and you can draw here NAND NAND. NAND NAND. So function app XYZ, directly can I write 1 2 4 7, and 1 2 4 7 is nothing but X XOR Y XOR Z. Can I write? Now what is the second function? F2 function XYZ is nothing but mean term of 3 5 6 7, and mean term of 3 5 6 7, what you can write? XY plus YZ plus XZ. This will be the answer. Already this is nothing but full adder circuit. So this is nothing but full adder circuit. Full adder circuit by PROM. Clear this thing? Later I will text previous year exact question. Don't worry for that. Clear? Now in today's section, decoder as well as modified decoder, you can say ROM and PROM, should be very clear to you. Okay. In next session we will discuss encoder circuit, multiplexer circuit and demultiplexer circuit. Okay, so tomorrow I will start. If anybody have any doubt, just ask me. If anybody have any doubt, just ask me. Please ask me if anybody have any doubt. Okay, if anybody have any doubt, ask me. Otherwise, I am going to stop today's session. Again, tomorrow we will start. We will start the next part. Okay, if anybody will ask you, what is the advantage of decoder? What answer you will provide? The main advantage of decoder is you can represent any memory location by easily with the decoder circuit. This is the main advantage. And second, you can implement any boolean function by using decoder. But what is the disadvantage, you know? And that disadvantage is again removed by this PROM. Now, is there any disadvantage with PROM? We don't have any disadvantage with PROM. That's why in today's world, we are going to use this circuit. This is not a programmable read-only memory. You don't treat this circuit as a memory. This you can say is a memory structure. This is a one standard structure and the name of structure is PROM, and PROM structure is always same. That's why generally students treat ROM means read-only memory and that is only used for the memory. No, this you can use for to implement any boolean function. I hope this thing is clear to you. Okay. Ready? So today's session I am going to stop. Tomorrow again at same time again we will meet. Okay. Thank you and bye bye. Okay, thank you.